Okay, Professor.
Yes, thank you. What is the paper? Today we would like to start to ask ourselves the following question. The question is as follows. Why in the world we need natural frequencies? Okay. Why did we spend so much time on beautiful functions K1 alpha x, K2 alpha x, K3 alpha x, K4 alpha x, and found omega 1 square, omega 2 square, omega 3 square, etc. I actually could have postponed the answer to this question, but I would like to answer now, and later we will deal with more determination of frequency in the course. What is this topic number? $21? Okay. Mr. Casey, is this 21? You don't number? 21. Okay, so therefore we will consider a realistic case, a realistic problem. And problem is like this. Say there is this beam, simply supported beam, and it is excited by such a load. Imagine that this load is, say, Q of x, t, and this is some, let us imagine, some constant, Q0, and then there is some function, phi of t, or f of t. So there is some given function, f of t. So our governing, so we want our governing differential equation is EI, force derivative of W with respect to x, plus rho A d2W dt square, and this equals Q0 f of t. Or we can actually consider even simpler case. We will come back to this. We will come back to it. And that is like this. And imagine that there is such a load. So that is, say, Q of x, t, equals Q0 sine pi x over L. And then there is some f of t. So that is what happens. So in this case, my governing differential equation will be d4w dx in force power plus rho a d2w dt square. This equals q0 sine pi x over L f of t. Now we found that this beam, when there is no forcing, no force, has mode shapes, which is like this. W k of x equals sine k pi x over L. Okay, we determine this. And natural frequencies. Which are omega k squared equals like this, EI over rho A, then K pi over L squared. Force power. Okay, that is what we found before. For simply supported case, we considered simply supported case for a long period of time, and that is what we found. So now we take our governing differential equation. Let us call it, this equation is a star. And in this governing differential equation, I'm looking for the solution like this. Wxt equals summation k from 1 to infinity. And then solution is in terms of mode shapes, wkx. And then some constant, that is a, some constant, ak. Or actually we can write down that this is some function, phi k of time. And then we will leave it at this, phi k of time. Now I can substitute this back into this governing differential equation, and I will get EI, force derivative with respect to x. So then, first of all, will be summation, k from 1 to infinity. Then wk force derivative times phi k of t. And then we have plus rho a. And then summation k from 1 to infinity. And then we have second derivative with respect to t. That means that wk will stay as is. And then we have d2 phi k dt squared. And this equals q sub 0 sine pi x over L f of t. Now, wk of x is a mode shape. Mode shape. Now, what does it mean it is a mode shape? It satisfies this equation. Okay? It satisfies the following equation. EI d4wk dx in force power minus rho a, then omega k squared wk equals 0. Look, it is obtainable from here. Okay, from here. Z should be thrown away. Then I have to substitute cosine omega t. Then I will get omega k. Omega k is a case natural frequency, and then instead of w, I have wk. So that is how we found mode shapes. That is a problem that we solved, if you remember. We denoted, if you remember, just reminder for your information. Rho a omega k squared over ei, we denoted as alpha in fourth power. And then we had this k1 alpha x and kj alpha x, etc. So the interesting thing is from here that fourth derivative of the mode shape equals rho a over ei omega k squared wk. So that is an expression. Fourth derivative of the mode shape is proportional to the function. So we can write it down. Fourth derivative is proportional to wk. So therefore, this could be substituted here. Not here, but here. Okay, and so I will get that. Can I cover this page here? Did we write this? Say it again. Yep. Mode, fourth derivative of mode shape is proportional to mode shape. Is proportional to mode shape. So then the fourth derivative expression could actually be substituted here, or just ei. So this expression then will be, look please, let us denote this equation 1. Will be ei, fourth derivative. So it equals rho a omega k. So here we get, look please, summation k from 1 to infinity omega k squared, okay, rho a, and wk, and then phi k of t. Then plus rho a, wk, second derivative with respect to t, k from 1 to infinity, and this equals q0 sine pi x over L f of t. So I'm left with this equation. Okay, first of all, pay attention, omega k suddenly appeared. Okay, because I used mode shapes. And then what I get is as follows. So I will substitute this wk. Wk is sine k pi x over L. So I substitute there and I get k from 1 to infinity. So there is this rho a here and rho a is there. So I can take that out. Okay? Then we have omega k squared, and then here we have sine k pi x over L, phi k of t, plus. So this is also, actually this sign I could have taken out, pay attention. Sine is here also, plus rho a. Oh, this rho a I took out. So sine is, so d2 phi k dt square here I have sine k pi x over L. This equals Q0 sine pi x over L f of t. Okay? Now I will multiply everything, left-hand side and right-hand side, by sine m pi x over L. M pi x over L. So where m is any number. Then I integrate from 0 to L dx. So I will get k from 1 to infinity, rho a, omega k squared, phi sub k of t, plus d2 phi sub k dt squared. Then I have integral sine k pi x over L. No, here I have sine, k pi x over L, times sine m pi x over L dx between 0 to L. And this equals integral q sub 0 from 0 to L sine pi x over L sine m pi x over L f of t dx. It's a rather cumbersome expression. But it simplifies in a terrific manner. And I'll show you how. Did we write this? Not yet. So we can check that the following is happening. This integral from 0 to L, sine k pi x over L, sine m pi x over L dx. This integral equals 0 if k does not equal m. If this k does not equal m, so these two numbers should be equal each other, otherwise it is 0. And equals L over 2 if k equals m. So what is our homework assignment? Number? Homework 11. So check that sine k pi x over L sine m pi x over L dx equals 0, k does not equal m, and equals L over 2k equals m. Please write down this homework. Just that is integral from 0 to L. Okay, we will be continuing with more homework. So now if this is the case, then in this sum on the left hand side, summation, k from 1 to infinity, all terms are 0 except when k equals m. Because look, this integral, k runs from 1 to infinity. M is fixed. M is fixed. So all the terms equal 0 unless k equals m. When k equals m, this is L over 2. So then we get here, pay attention, here we get rho A. So there is no summation anymore. Here we have omega sub m squared phi sub mt plus d2 phi sub m dt squared times L over 2 equals q sub 0 can be taken out. Integral from 0 to L sine pi x over L sine m pi x over L f of t dx. Now this integral is also the same. This integral sine pi x over L sine m pi x over L dx. Okay, let us leave this integral first. Let us leave this integral. So this is, we denote q sub 0 and then I m f of t. This I m is integral. Okay, that is how I denote it. So then I got the following equation. Look, please. d2 phi k, d2 phi m, dt squared plus omega sub m squared phi m equals q sub 0 divided by rho a, I sub m f of t. I got this equation. Now, what is this equation? This equation is very, very close to mx double dot plus kx equals some f of t, some coefficient, coefficient b. That is second derivative plus kx. So there is this function plus this. Here m is arbitrary number. M is 1, 2, 3, etc. So what we got an equation for 1 degree of freedom system. With frequency omega sub m. So some conclusions. I did not solve this problem yet. 5. Conclusions. All natural frequencies are dancing on the wedding of beam vibrations. This is one thing. See, all natural frequencies are there, omega 1, omega 2, omega 3, etc., because I have many equations like this. if I have forced vibrations, then natural frequencies of free vibration are appearing there. It's also an unbelievable conclusion. Okay? To solve forced vibration problem, we need free vibrations too. It's also an unbelievable conclusion. That is why we did not just spend our time on natural frequencies just because we were interested, like Pythagoras was interested with natural frequencies, but he was interested for its own sake, natural frequency for some harmonic considerations, etc., not for any forced vibration reasons. But as often happens in science, first scientists are interested with something for its own sake. Later, that something which was developed for its own sake finds an unbelievable application for some practical problems. It nearly always happens like this. Okay, that is one thing. Second thing, pay attention. Third conclusion, M equals 1, 2, 3, etc. Okay. Beam vibrations are equivalent to infinite number of single degree of freedom systems. Okay, that is also unbelievable. Look, we are coming from one unbelievable conclusion to another unbelievable conclusion. Because we have infinite number. M goes from 1 to infinity. For each M, this is 1 degree of freedom system. So, what we can say is that this beam is actually equivalent to like this mass. So the M1, K1, then M2, K2, then M3, K3, etc. Many things like this together. Somehow they are combined together, and these things combined are equivalent to this beam. So what we can say is that natural frequencies are needed to find response of the system. Of the system. So natural frequencies are actually intermediate step. Natural frequencies are intermediate step in order to find the response. Any questions? So then, let us go back to the equation d2 phi m dt squared plus omega m squared phi m equals q sub 0 rho a I m f of t, where what is I m? I m is sine pi x over L, sine m pi x over L dx from 0 to L. Now, we just said before that if I have k pi x, and this k should equal m, but this k is 1, actually. There is 1 here. So this integral actually equals 0 if m does not equal 1, and equals L over 2 if m equals 1, in this case. So in the general case, you have infinite number of things. But in this particular case, that is what we have. So therefore, m must equal 1. So therefore, we have d2 phi 1 dt squared plus omega 1 squared phi 1 equals q sub 0 rho a I1, which is L over 2, f of t. Now imagine that f of t is just a constant. Let f of t be a constant, say b. And then we have second derivative of phi 1 plus omega 1 squared phi 1 equals q sub 0 rho a L over 2b. Now this is a non-homogeneous equation. So therefore phi equals phi of t c1 cosine omega 1t plus c2 sine omega 1t plus particular solution, which would be this divided by this coefficient. So it will be q sub 0 rho a L over 2b divided by omega 1 squared, constant. So we saw if load is like this, like a first mode, then beam reduces to 1 degree of freedom system. Yes, sir. Oh, here. If load is like first mode, like I had today, then beam reduces to 1 degree of freedom system. So I will assign you second work. Consider beam under load. So that is 11.1, that is 11.2. Under load like this. So that is like this. Q of x t equals q sub 0 sine 2 pi x over L cosine 5t. Okay, find response. Which means find W x t. Yes, that is a mode 2. This is mode 2. Second mode of free vibration. Now I will distribute this homework. That is yours. That is yours. I think you need to give me more, no? It seems to me. I thought that is what I have. Did you give me more? I see. I have to search. I have to search. Maybe by chance it is inside. See, okay. I will search. Yeah, these are new ones. Yes, I hope. Okay, first of all, some of the students who are here do not. They do not come always to this office. They are looking at Blackboard. Is it right? You are getting these lectures. Did you ever go to Blackboard? You can get these lectures also online. Did you check? Who checked that? Oh, you did not watch because you are watching here. Did you see? Sometimes you review. Okay. Now there, why I'm bringing you this, because I put this, I gave you something in writing in the beginning, but this is also available on the Blackboard. You may want to copy this. So description of the course, mechanical vibrations, name of the lecturer, telephone, fax, email, website, Google, textbook, notes and this book, office hours, attendance. Then there is this grading system as well as common course syllabus. So this all is available on the Blackboard, and I would like you to go. Why I did not, it would be very easy for me to copy, but I was asked to request from students to go and use this Blackboard. Otherwise, students are not going to Blackboard. Yes, sir. Yes, I will inform you, hopefully next time. We would like to do first test before the spring break. Say it again. Okay, we will discuss, I will discuss with you because there are, how many tests do we have? I think 2, is it not? Yeah, 2 tests. So I thought that it was nice to do it one in the first part and the other in the second part. Otherwise, if I do say immediately after you come from spring break, then maybe during spring break that will be too much pressure on you. But we will discuss later, if you don't mind. We will discuss later. So I would like you to get the copy of these sheets of paper. Second thing, we would like to do something more now. The only thing I did not, do you know the course number? Oh, 62. And the other? So we have here some graduate students and undergraduate students. So 6223. Okay, then I will write down. We have to do something which is not an evaluation of the professor, but some suggestions on improvement and other things. But the thing that was given to me does not have correct numbers. So 60, 23, graduate. So maybe you distribute to these 3 people, and after that you have to sign here and close this. And then maybe you're going back to the mechanical engineering, to that building? Not today. You are going because you have so maybe we will give to her. No. She will, you can fill this and she will give to the secretary in mechanical engineering. Yes, because and you will do then here. Do you remember the number?
No.
Oh.
You might know when they're used to put it up there.
Oh, okay. I don't know, 4220, I don't know, that is what is, I wrote on top of, and in any way, mechanical vibrations undergraduate. I will ask them. Please, 2 people, unfortunately we don't have, so you fill now and put it there, and you 2 fill, and I will ask the number. Do you know the number of the course in this course?
We have the course number.
Yes.
Let's see here, but not the.
4222. Okay, 4220.
Yeah,
Thank you very much. Yes, that is correct. 4220 is correct. Graduate was not correct. So I will look in that way. So all lectures are available on Blackboard, of course. Which was why in the world we need natural frequencies. Natural frequencies actually per se, as such, we don't need. We don't need natural frequencies for their own sake. We need natural frequencies because they appear in forced response calculations. Maybe you have any questions or discussions on this? Because that sounds a bit strange. Why it could sound strange? Because, look please, natural frequencies deal with free vibrations naturally. There is no loading. It turns out that we found that beam has infinite number of natural frequencies, omega 1, omega 2, etc. Now when we deal with the response, these natural frequencies are very handy because we are expanding the solutions in terms of the modes. These modes happen to be very good tool for expansion. One could have said, okay, maybe I don't know the mode. I'm not going to expand then in terms of the mode. But there are already, we say, for uniform beams, I gave you already modes. In today's homework, I did ask you to find some mode shape for a particular case. So for non-uniform beams, finite element method provides these mode shapes. So therefore, mode shapes of free vibrations are always there, always available. Then we expand the solution in terms of these mode shapes. Why mode shapes? Maybe something else. Mode shapes satisfy all boundary conditions. W should satisfy also all boundary conditions. Therefore, it is natural to expand W in terms of functions that already satisfy all boundary conditions. Does not make sense to expand in terms of functions that, for example, do not satisfy boundary conditions. Now, you could say, okay, I'm ready to expand in terms of functions that satisfy boundary conditions, but maybe not of mode shapes. Okay, one could have asked such a question. We will do that later. We will do that later. But still, mode shapes will be, even in that case, suddenly natural frequency and mode shape will be coming into play. You may want to summarize this somehow. Mr. Casey, can you sign this? You already signed. Okay, then maybe you give to that student. Unless you are going there also. No. Okay, then, because it's easy to transfer. We don't need two people to go. Just one person is enough. So mode shapes are very powerful, actually we can say mathematical tool for solving forced vibration problems. Oh, you did not put? You did not? Okay, I will wait because I must conduct this